Incorporating capabilities like vision or natural language understanding into a software application was historically an immense time-consuming engineering hurdle. Before writing a single feature, developers had to provision and maintain complex GPU instances to provide the necessary raw computation. There was also a significant data preparation burden, requiring teams to manually clean and format noisy datasets before they could be used for training. Finally, the process required specialized data science teams to manually tune model weights, often through months of trial and error. This traditional approach resulted in significant infrastructure overhead and technical debt, frequently stalling the deployment of new software. AWS managed AI services offer an alternative that bypasses the need for custom infrastructure. These are fully pre-trained machine learning models designed to solve specific use cases out of the box. Interaction with these capabilities occurs through standard API calls, eliminating the requirement of complex, custom data pipelines. Because the underlying hardware is abstracted, developers do not need to provision or manage the host servers. This architecture shifts the primary engineering focus from low-level data science mechanics to the integration of managed services. This comparison illustrates the engineering trade-offs between building a custom model and calling a managed service. On the left side, the custom workflow is constrained by the friction of manual data preparation and repetitive training loops. There is also significant operational risk. During traffic spikes, the team must manually manage load balancing and server latency. Conversely, the API-driven architecture on the right streamlines data routing. Raw data hits a unified gateway and returns a prediction without individual server management. From an operational perspective, this entire flow functions as a serverless environment. Where a custom model might take many months to successfully deploy, a managed API endpoint is accessible in milliseconds. This architectural shift allows developers to prioritize business logic over server maintenance. While the developer only sees the API, AWS operates a vast physical infrastructure to maintain responsiveness. These services utilize multi-AZ deployments, distributing the workload across multiple availability zones. If one data center experiences an outage, automatic failover routing instantly shifts traffic to a healthy node without interrupting the API call. Regional redundancy further ensures high availability for applications operating at an enterprise scale. This hidden layer also includes clusters of highly optimized CPU and GPU hardware. Unlike general-purpose computers, these clusters are specifically tailored for low-latency inference. By calling the API, a developer instantly inherits these failover systems and specialized hardware architectures. The financial model for these services is designed to support this flexible scale. The default is a pay-per-use model, where billing is calculated based on precise token or transaction counts. This eliminates the cost of idle resources when the application is not in use. For larger, more predictable workloads, AWS offers provisioned throughput. This model allows enterprises to guarantee capacity and control costs for high-volume production traffic. In both cases, infrastructure costs align directly with actual usage, reducing the risk of over-provisioning hardware. This ecosystem is organized into specific cognitive domains, such as the speech and audio layer. Amazon Transcribe handles audio ingestion, converting raw voice into structured text. To handle industry-specific jargon, you can provide the service with custom vocabularies. It also includes speaker diarization, which identifies different participants in a single recording. Security features are built into the API, allowing for automatic redaction of personal information and the detection of toxic language in voice data. For audio output, Amazon Polly converts text into natural-sounding speech. You can use pronunciation lexicons to ensure brand names or specialized terms are spoken correctly. Through speech synthesis markup language, or SSML, developers can also adjust the cadence, breath, and emphasis of the voice. These tools provide a complete conversational layer without requiring specialized audio engineering. Panning over to the vision layer, we find Amazon Recognition. Recognition provides out-of-the-box face analysis and object detection capabilities. When general models are insufficient for a niche task, developers can use Recognition custom labels. This allows for the identification of specialized items, like specific machinery or medical anomalies, without training a model from scratch. The service also includes a content moderation workflow to automatically flag non-compliant visual data. For sensitive data or ambiguous edge cases, the system uses a human-in-the-loop oversight model. Amazon A2I routes these specific cases to a human review team for final verification. This vision ecosystem integrates automated identification at scale with configurable human validation. Viewed as a whole, these services form a comprehensive cognitive ecosystem. They function as secure, highly available building blocks for modern applications. By orchestrating these nodes, you can create multimodal workflows, such as extracting text from a video and translating it into a different language for audio synthesis. This modular approach reduces deployment timelines by removing the requirement to train models and manage server clusters. Architects can now leverage built-in multi-AZ and regional redundancy as standard components of their system design. They can also optimize for cost by selecting the billing model that best fits their specific workload. Ultimately, building for machine intelligence has transitioned from isolated data science tasks to a challenge of robust systems integration and API orchestration at scale.